Welcome to Tech 560, where we embark on an exciting journey into the world of distributed systems. In this masterclass, we will explore how to design, debug, and operate systems capable of serving millions of concurrent users while maintaining predictable performance and resilience, even in the face of partial failures. As engineers at the L8 and distinguished engineer levels, you will be tasked with architecting systems where a single bottleneck can lead to significant costs, both in terms of infrastructure and user trust. You will learn that failure modes often only become apparent when systems are operating at production scale, under real traffic patterns, hardware faults, and even adversarial load conditions. Throughout the course, we will break down this complex journey into manageable chapters. We will start with the limits of vertical scaling and progress through the intricacies of horizontal distribution. You will gain insights into data partitioning, GPU orchestration for large language model serving, and the identification of network and storage bottlenecks. We will also delve into observability and failure recovery strategies that separate robust production systems from mere prototypes. Understanding how to scale to millions of users requires a shift in perspective. It's crucial to recognize that systems are not just collections of independent services. Instead, they are interconnected graphs of compute, memory, network, and storage resources. Each layer of this architecture imposes its own latency budgets and throughput ceilings. For instance, consider a single server architecture that handles an inference request for a large language model. It must contend with various factors like GPU memory bandwidth, which can reach up to 3.35 terabytes per second on an H100 GPU. There are also PCIe transfer rates that can hit 64 gigabytes per second, and we have to factor in CPU to DRAM latency, which is about 100 nanoseconds. Additionally, network round-trip times can vary significantly, being less than a millisecond within a data center, but stretching to 20 to 100 milliseconds when crossing regions. As we scale horizontally, we face new challenges. The introduction of distributed state brings complexities such as consensus overhead, replication lag, and the risk of partial failures. A single slow disk, a misconfigured network interface card, or even a garbage collection pause can lead to noticeable latency spikes or even loss of availability for users. The interplay between hardware and software is vital in determining which resource will reach its limit first, whether it's GPU compute, memory bandwidth, network fabric, or storage IOPS. For example, serving a large language model with 70 billion parameters requires around 140 gigabytes of GPU memory in FP16 format. This necessitates the use of multi-GPU tensor parallelism and careful management of all reduced bandwidth during both the prefill and decode phases. In addition, Kubernetes orchestration introduces its own latencies, such as scheduler delays and overhead from container network interface plugins. When we look at production systems like ChatGPT, they operate on thousands of GPUs, employing request routing, batching, and preemption strategies to maximize throughput while adhering to strict latency service level agreements. As we scale, the primary bottlenecks evolve. Single server systems typically hit CPU or GPU compute limits first, followed by memory bandwidth as batch sizes increase. In distributed systems, we encounter limits related to network bisection bandwidth, storage IOPS, and coordination overhead in consensus protocols. At the level of millions of users, we also have to contend with long-tail latency caused by stragglers, which are the slowest 1% of requests that disproportionately affect performance. We face challenges like thundering herds during cache invalidation and correlated failures, where entire availability zones might lose power or network connectivity simultaneously. Your role will be to identify which bottleneck is most critical at each stage of scaling, ensuring that you provision enough headroom before reaching saturation. Additionally, you will design fallback paths that allow the system to degrade gracefully rather than fail catastrophically. As we move forward, we will explore various chapters that will deepen your understanding of these concepts. From analyzing hardware bottlenecks to mastering data partitioning and sharding strategies, and from optimizing GPU orchestration to improving observability and performance debugging. This masterclass will equip you with the skills and knowledge necessary to tackle the challenges of designing and operating distributed systems at scale. Let's get started on this exciting adventure. Welcome to this segment of Tech 560, where we delve into the limitations of vertical scaling in computing. In this chapter, we will explore the physical and economic constraints that come into play when we try to enhance a single machine's capabilities. We will examine several critical factors, including the bandwidth limitations of PCIe, the throughput ceilings of NVMe drives, the walls of memory bandwidth, and the bottlenecks that can occur with GPU interconnects. As you progress through this chapter, it is essential to understand when it becomes economically unfeasible to simply add more resources, like additional cores, memory, or faster storage, to a single machine. We will also discuss how to assess workloads effectively, allowing you to classify them as compute-bound, memory-bound, or I/O-bound. This classification will help you determine the point at which horizontal scaling, distributing workloads across multiple machines, becomes a more cost-effective solution compared to vertical scaling. To set the stage, let's consider the hard limits of vertical scaling. A modern dual-socket server, equipped with either Intel's Sapphire Rapids or AMD's Genoa processors, can theoretically support up to 128 physical cores, 6 terabytes of DDR5 memory, and 24 NVMe drives. However, each of these resources has its own limitations. For instance, DDR5 memory can deliver a theoretical maximum of 1.6 terabytes per second in bandwidth, but in real-world scenarios, due to factors like NUMA effects and contention for memory controllers, you might only achieve around 1.2 to 1.4 terabytes per second. This means that if your application relies on random access patterns across large data sets, you may hit the memory bandwidth wall long before you fully utilize your CPU's processing power. Now, let's talk about PCIe. The PCIe Gen 4 interface, which can provide 64 gigabytes per second of bidirectional bandwidth, is shared among all devices connected to the same PCIe root complex. For example, a single NVIDIA H100 GPU can generate an impressive 3.35 terabytes per second of internal bandwidth using HBM3 memory. However, when transferring data between the host memory and the GPU memory, you are constrained by that 64 gigabytes per second PCIe limit. This creates a significant bottleneck, particularly for large language model inference workloads, where the model weights may exceed the GPU memory capacity. Here, the disparity between the on-device compute capabilities and the host-to-device transfer speeds can result in a staggering 52-fold bottleneck. Moving on to NVMe SSDs, they can deliver sequential read speeds of up to 7 gigabytes per second for Gen 4 drives and 14 gigabytes per second for Gen 5 drives. In a server with 24 NVMe drives, you might expect an aggregate bandwidth of 168 gigabytes per second. However, due to the PCIe topology, real-world performance often caps out at around 80 to 100 gigabytes per second, primarily because of contention and the overhead of CPU cycles used for handling I/O interrupts. In terms of inference workloads, the CPU can quickly become a bottleneck, especially when dealing with small batch sizes and latency-sensitive tasks. For instance, a single core running optimized inference for a BERT-based model might achieve between 200 and 400 inferences per second, while consuming around 15 to 20 watts. If you scale that up to 128 cores, you could see throughput rise to 25,000 to 50,000 inferences per second, but this would also increase power consumption significantly. In contrast, a single H100 GPU running the same model at a batch size of 128 can deliver between 80,000 and 120,000 inferences per second. But if you drop down to a batch size of 1 for real-time serving, GPU utilization can fall to just 15 to 25%. In these scenarios, CPU-based serving with multiple cores may actually be more cost-effective due to lower idle power consumption and better multi-tenancy. Lastly, let's touch on the economic aspects of scaling. The tipping point for horizontal scaling occurs when the cost of upgrading a single powerful machine surpasses the cost of adding two smaller machines that can provide similar aggregate capacity. For example, a high-end 128-core server with 6 terabytes of RAM might cost between $85,000 and $110,000. In contrast, purchasing two 64-core servers, each with 3 terabytes of RAM, could cost between $50,000 and $65,000 combined. This dual machine setup not only provides additional network and PCIe bandwidth, but also eliminates the penalties associated with NUMA, resulting in improved effective throughput for distributed workloads. As we wrap up this overview, remember that understanding these limitations and economic considerations is crucial for making informed decisions about scaling your computing resources effectively. In the next sections, we will dive deeper into practical calculations and strategies for optimizing workload distribution. In this chapter, we will explore the concept of horizontal scaling, which is a strategy that distributes the workload across multiple identical nodes instead of relying on a single, more powerful machine. This approach presents unique challenges, particularly when it comes to managing state. Stateless services can easily scale through replication, meaning you can create multiple copies of the service without worrying about maintaining any session information. However, stateful systems, which do maintain session data, require more complex strategies for partitioning data to balance the load while still ensuring consistency. To illustrate this, let's look at Discord's architecture. Discord efficiently handles over 1 million concurrent WebSocket connections by sharding users across gateway servers. This sharding is done using a deterministic hash of the user ID modulo, the total number of servers. This ensures that each user consistently connects to the same server, maintaining their session state without disruption. Now, when we talk about partitioning data, one of the challenges we face is what we call the rebalancing problem. If we use a naive modulo-based approach to partition our data, adding or removing nodes can lead to a situation where nearly all keys are reassigned to different servers. This can create significant issues, such as cache invalidation and increased latency. Instead, we can use a technique called consistent hashing. This method maps both the nodes and the keys onto a circular ring using a hash function. When we add a new node, only a small portion of the keys need to be reassigned, which minimizes disruption and maintains stability. For example, Redis cluster uses consistent hashing with 16,384 hash slots distributed across its master nodes. This setup allows it to achieve an impressive throughput of 1 million operations per second by parallelizing operations across different shards. Each key is mapped to a specific slot using a CRC16 hash function, and clients maintain an updated mapping of slots to nodes, ensuring efficient access to data. As we delve deeper into distributed systems, we encounter the CAP theorem, which tells us that we cannot guarantee consistency, availability, and partition tolerance all at once during network splits. In practice, partition tolerance is essential, which forces us to choose between two options: CP, which stands for consistent but unavailable during partitions, or AP, which is available but may allow for inconsistencies. For instance, Google Spanner is an example of a CP system that uses GPS and atomic clocks to maintain consistency across data centers, accepting the trade-off of occasional unavailability. On the other hand, Cassandra exemplifies an AP system, allowing for tunable consistency, where we can choose how strict our consistency needs to be, often defaulting to eventual consistency. When it comes to sharding strategies, careful consideration is needed to avoid hotspots. For instance, PostgreSQL implements logical replication for read scaling, where write-ahead logs are streamed to read replicas, typically maintaining a lag of under 100 milliseconds. However, when you write to a primary node, the reads can be distributed across replicas, but this requires careful handling of replication lag in your application logic. For write scaling, you might shard based on a partition key, such as user ID or tenant ID. However, poor key selection can lead to imbalances in load distribution. For example, Instagram uses a modified Snowflake ID scheme for sharding by user ID, ensuring that the first part of the ID represents a timestamp, while the next part indicates the shard ID. This method not only helps distribute the load, but also preserves the chronological order of events within each shard. Coordination protocols like Raft and Paxos are crucial for maintaining strong consistency in distributed systems. Raft, for example, replicates a log across multiple nodes and requires a majority acknowledgement before committing any entries, ensuring linearizability but at the cost of increased latency. This protocol is used by etcd, which supports Kubernetes cluster state management. In summary, understanding these concepts is vital as you design systems that can handle millions of requests per second while maintaining the necessary consistency and availability. By mastering horizontal scaling, consistent hashing, and the CAP theorem, you will be well equipped to tackle the challenges of modern distributed systems. In this chapter, we will explore the intricate world of load balancing architectures, particularly those capable of distributing over 10 million requests per second across diverse server fleets while ensuring minimal latency. This is crucial for high-performance systems, especially at advanced engineering levels, where understanding the nuances of failure modes in hashing algorithms, kernel-level limitations that can lead to port exhaustion, and the differences in packet processing between Layer 4 and Layer 7 approaches becomes essential. Load balancing operates on two primary layers, each with distinct characteristics. Layer 4 load balancers function by examining TCP or UDP headers, making routing decisions based solely on IP addresses and port numbers, without delving into the actual application data. A notable example is Google's maglev, which can handle an impressive 10 million packets per second per core. It achieves this through a specialized technique called kernel bypass, utilizing the Data Plane Development Kit, or DPDK. Maglev maintains connection states in a lock-free hash table with over 655,000 buckets and employs a consistent hashing method to efficiently manage backend servers. This method ensures that when backends are added or removed, less than 1% of the data flows need to be rehashed, minimizing any potential disruption. On the other hand, Layer 7 load balancers take a more in-depth approach by terminating TCP connections and inspecting HTTP headers. They make routing decisions based on various factors, such as URL paths or cookies. However, this deeper inspection means that Layer 7 balancers typically handle fewer requests, around 100,000 to 500,000 per core, compared to their Layer 4 counterparts. The choice between using a Layer 4 or Layer 7 load balancer often hinges on specific routing requirements and acceptable levels of latency. Layer 4 balancers may introduce a latency of 50 to 200 microseconds when using direct server return mode, allowing backend servers to respond directly to clients. In contrast, Layer 7 balancers can add a latency of 1 to 5 milliseconds due to the overhead of full TCP termination and HTTP parsing. One critical concept we will discuss is consistent hashing, which plays a vital role in preventing cache stampedes during node failures. In traditional hashing, when a node fails, all keys are reassigned, leading to a situation where many requests simultaneously hit the database. However, consistent hashing mitigates this issue by mapping each physical node to multiple points on a hash ring. This means that when a node fails, only a fraction of the keys need to be remapped, distributing the load across surviving nodes instead of overwhelming a single successor. Another important topic is the prevention of ephemeral port exhaustion, which can occur when a client establishes too many outbound connections. Each TCP connection consumes a unique combination of source IP and port, along with destination IP and port. If all the source ports are allocated, new connection attempts will fail. Techniques like HTTP 1.1 connection reuse and HTTP 2 multiplexing help alleviate this issue by allowing multiple requests over a single connection, significantly reducing port consumption. We will also touch on DNS-based global load balancing, which directs traffic across different geographic regions. However, it has limitations due to its long time-to-live settings, which can lead clients to continue sending traffic to a failed data center long after DNS records have been updated. In contrast, Anycast routing with BGP provides faster failover by advertising the same virtual IP from multiple locations, although it requires careful coordination and can lead to connection resets during failovers. As we move forward, we will examine key insights and trade-offs in load balancing, including common production failure modes and their impacts on performance. Understanding these concepts will empower you to design robust multi-tier load balancing systems that can gracefully handle partial outages and maintain high performance under varying conditions. In this chapter, we delve into the intricate world of caching, exploring its complete hierarchy from the CPU's cache layers all the way to application-level distributed caches and edge content delivery networks, or CDNs. This is a crucial topic because at a large scale, caching is not just an optimization, it becomes a fundamental requirement for system architecture. For instance, services like Twitter's timeline can achieve an impressive 99.7% cache hit rate, allowing them to serve 6,000 tweets per second while drastically reducing database load by 95%. By the end of this chapter, you will be equipped to design multi-tier caching architectures that effectively address common challenges such as cache penetration, cache avalanche, and the hotkey problem. You will also learn how to maintain consistency guarantees that align with your specific read-write ratios and latency service level agreements. Now, let's break down the memory hierarchy, which spans a staggering 6 orders of magnitude in latency. At the top, we have the CPU's L1 cache, operating at just 0.5 nanoseconds, followed by L2 at 7 nanoseconds and L3 at 20 nanoseconds. As we move down, we encounter main memory at 100 nanoseconds, local SSDs at 150 microseconds, and then Redis over local host at 200 microseconds. Remote Redis takes about 1 millisecond, while a database query can take anywhere from 10 to 50 milliseconds. Finally, the CDN edge can take 10 to 100 milliseconds, depending on geographical factors. Each layer in this hierarchy balances capacity against speed, and it's essential to understand this trade-off. For example, a modern Intel Xeon processor features a modest 32 kilobytes of L1 cache per core, 1 megabyte of L2 cache, and 36 megabytes of shared L3 cache, alongside a whopping 512 gigabytes of DRAM. Your application cache might utilize 100 gigabytes in Redis, or even 10 terabytes in a distributed cache like EVCache from Netflix or Pelican from Twitter. At the CDN edge, the capacity can be effectively unlimited. A key principle to remember is inclusion. Higher cache layers store subsets of the data from the layers below them. This means that when we achieve a high hit rate in the upper layers, it compounds positively for our overall access rate. For instance, if the L1 cache hits 95% and L2 hits 80% of L1 misses, while L3 hits 70% of L2 misses, the effective access rate for DRAM becomes just 0.3% of requests. Next, we need to consider eviction policies, which dictate what remains in the cache when we face capacity constraints. The least recently used, or LRU, policy is often the go-to choice since it approximates optimal behavior for workloads that exhibit temporal locality. It operates efficiently with O1 time complexity using a combination of a hash map and a doubly linked list. Redis implements a variant of LRU that samples a few keys to reduce memory overhead while still approximating LRU behavior. On the other hand, the least frequently used, or LFU, policy can outperform LRU in scenarios where certain items see disproportionate access. Redis's LFU uses an 8-bit logarithmic counter to track access frequency, allowing it to prioritize popular items even if they haven't been accessed recently. We also have more advanced policies like Adaptive Replacement Cache, or ARC, which uses 2 LRU lists to balance recency and frequency, but it comes at the cost of increased metadata overhead and patent restrictions, limiting its widespread use. When it comes to write policies, we have several options that determine how we maintain consistency. Write-through updates both the cache and the backing store simultaneously, ensuring consistency but introducing additional latency. Write back, however, updates the cache immediately and defers writing to the database, which can lead to faster write operations but also carries the risk of data loss in case of cache failure. Another approach is write around, which bypasses the cache on writes and only populates it on subsequent reads, making it suitable for scenarios where the likelihood of rereading after a write is low. Cache aside, or lazy loading, relies on the application to manage cache behavior, fetching data from the database on a cache miss and invalidating cache entries on writes. This method is popular because it decouples the cache from the database schema, allowing for more flexibility. Time to live, or TTL settings, are also crucial as they balance data freshness against the load on the database. Selecting the optimal TTL can minimize database load while still adhering to staleness requirements. For example, Twitter uses a 5-second TTL for home timelines, which experience a high write rate compared to a 60-second TTL for user profiles, which see less frequent updates. Finally, we must consider the production failure modes that can arise in caching systems. Cache penetration occurs when requests for non-existent keys bypass the cache, leading to excessive database queries. Cache avalanche happens when many cache entries expire simultaneously, overwhelming the database with requests. Lastly, the hotkey problem arises when a single cache key receives an overwhelming amount of traffic, straining the capacity of a single cache node. By understanding these concepts and the underlying mechanics of caching, you will be better prepared to design robust systems that can handle the demands of modern applications effectively. In this chapter, we will explore the important concepts of horizontal and vertical partitioning strategies, which are crucial for scaling databases that handle billions of rows and millions of writes per second. As you progress to the L8 level, you will be tasked with designing effective partitioning schemes. The goal here is to eliminate hotspots, minimize the need for cross-shard transactions, and maintain consistency guarantees, especially under network partitions. Let's start by understanding what database partitioning is. Partitioning is the process of splitting data across multiple physical nodes. This approach allows us to surpass the capacity limits of a single machine. Horizontal partitioning, often referred to as sharding, divides the rows of a database across different nodes based on a partition key. On the other hand, vertical partitioning involves splitting columns or tables. The key challenge lies in selecting a partition key that not only distributes the load evenly, but also keeps related data together. This is essential to avoid costly cross-shard queries. For instance, Uber's schemaless system has achieved an impressive throughput of 2.3 million writes per second by sharding data using the user ID as the partition key. They employ consistent hashing across 4,096 virtual nodes that map to physical MySQL instances. This ensures that all data for a specific user resides on the same shard. Additionally, when they add new nodes, they only need to move a fraction of the data, specifically 1/n of the total data, which significantly reduces the rebalancing effort. Now, let's talk about hash-based partitioning. This method applies a hash function to the partition key and uses either modulo or consistent hashing to assign rows to different shards. This technique provides a uniform distribution of data and helps eliminate hotspots. However, it does come with a downside. Range queries can become expensive because consecutive keys may end up scattered across different shards. Take Vitess, for example, which powers YouTube's MySQL infrastructure. It manages over 70 billion rows by using range-based partitioning on primary keys. In this case, explicit shard key ranges are defined within a topology service, which allows for efficient range scans and time series queries. However, this method requires careful monitoring to detect any skew in data distribution. Consider Instagram's experience when they sharded their database by user ID using an MD5 hash modulo 4096. They discovered that celebrity accounts generated significantly more data than the average user, leading to a 100-fold difference. To address this skew, they implemented a secondary sharding dimension based on the creation timestamp for their posts and media tables. When it comes to distributed transactions across shards, maintaining ACID guarantees can be quite complex. This is where protocols like two-phase commit or 2PC come into play. In a 2PC setup, a coordinator sends a prepare message to all participant shards, waits for their votes, and then issues a commit or abort command. While this method ensures consistency, it introduces latency, typically adding 10 to 100 milliseconds, depending on network round-trip times. A significant risk arises if the coordinator crashes after sending the prepare message, but before issuing the commit. In such cases, the participant shards remain locked, leading to potential availability issues. Google's Spanner addresses this challenge using the TrueTime API, which provides globally synchronized timestamps with an uncertainty of just 7 milliseconds. This allows Spanner to achieve external consistency without blocking. In practice, many large-scale production systems avoid cross-shard transactions altogether by designing their schemas carefully. For example, Facebook's Tao social graph store denormalizes friend lists and post metadata, ensuring that an overwhelming majority of queries hit a single shard, while accepting eventual consistency for rare edge cases. As we discuss query routing in federated databases, it's important to note that a proxy layer is necessary. This layer parses SQL queries, identifies which shards are affected based on the where clauses, and either executes scatter-gather queries or rejects queries that lack shard keys. Vitess's VTGate is a good example of this, as it parses queries and rewrites them for shard-specific routing, maintaining a query plan cache to minimize parsing overhead. However, for queries that span multiple shards, VTGate executes them in parallel and merges the results. Keep in mind that aggregations like count or sum require fetching all matching rows, which can be expensive. When rebalancing shards to add capacity, we must move data between nodes while ensuring that the system remains available. Consistent hashing with virtual nodes helps minimize data movement to just 1n of the total data when adding a new node. However, the actual data migration can take several hours or even days when dealing with terabyte-scale shards. Vitess handles resharding by creating new target shards, copying data from source shards using filtered replication, and then atomically switching traffic with a two-phase cutover process. This involves first switching reads, followed by writes once the replication lag drops below 1 second. During this transition, queries may need to access both old and new shards for a brief period. Now let's summarize some critical insights and trade-offs. A common production failure mode occurs when there's a hotspot shard due to a skewed partition key distribution. For example, celebrity user accounts or popular product IDs can create significant load imbalances, leading to one shard operating at 95% CPU while others remain relatively idle. This can result in latency spikes and connection pool exhaustion on the hotspot shard, potentially causing cascading failures if the application attempts to retry operations. Hash partitioning, while providing uniform distribution and straightforward rebalancing, negatively impacts range query performance and complicates querying by secondary attributes. In contrast, range partitioning allows for efficient range scans and can facilitate the dropping of old partitions for time series data, but it requires active monitoring for skew and manual intervention when ranges grow too large. When it comes to cross-shard transactions, the two-phase commit protocol introduces latency and can create. In this chapter, we are diving into the intricacies of GPU orchestration for large language model inference at a production scale. The focus here is on how we can effectively implement parallelism strategies, manage memory for key value caches, utilize batching techniques, and create a serving infrastructure that maintains incredibly low latency. Specifically, sub 100 milliseconds for 99% of requests, even when handling over 1,000 queries per second. As you advance in your studies, especially at the L8 or DE level, you will be expected to design systems that not only maximize GPU utilization, but do so efficiently, achieving over 80% model flops utilization. This means your systems should be resilient enough to handle traffic spikes, model updates, and even hardware failures without degrading the quality of service. To understand LLM inference at scale, we need to recognize that a single GPU often cannot manage the large models we are working with, especially those with over 70 billion parameters, which can require around 140 gigabytes of memory in half-precision format. Therefore, we orchestrate compute resources across multiple GPUs and nodes. There are three primary strategies for achieving this: tensor parallelism, pipeline parallelism, and data parallelism. Tensor parallelism allows us to split individual operations across multiple GPUs within a single node, typically using configurations like 8 A100 or H100 GPUs connected via NVLink. This method minimizes latency for single requests, adding only a small overhead compared to using a single GPU. However, it requires high bandwidth interconnects to function effectively. Pipeline parallelism, on the other hand, partitions the model layers across different GPUs or nodes. This approach trades some latency for increased throughput by processing requests in microbatches. While it can achieve high efficiency, it does introduce idle cycles, known as bubble time, as the system fills and drains the pipeline. Data parallelism replicates the entire model across different sets of GPUs, allowing us to scale query processing linearly. While this method can handle more requests, it does require careful load balancing and increases the memory footprint. Another crucial aspect of managing LLM inference is how we handle memory for the key value cache. In transformer models, attention mechanisms require storing key value tensors for all previous tokens processed. For instance, a 13 billion parameter model serving contexts of 2048 tokens consumes around 3.2 gigabytes of memory per request. This means that an 80 gigabyte A100 GPU can only support 20 to 25 concurrent requests before running out of memory. To address this memory challenge, techniques like VLLM's paged attention treat the key value cache like virtual memory. By dividing the cache into fixed-size blocks and allocating them non-contiguously, we can eliminate fragmentation and significantly enhance throughput, up to 24 times higher than traditional methods that allocate memory contiguously. Batching strategies play a fundamental role in determining the trade-offs between throughput and latency. Static batching waits for a fixed number of requests to accumulate before running inference, which maximizes GPU utilization but can introduce delays, pushing the P99 latency into seconds during variable loads. Continuous batching, however, processes requests at different stages of generation simultaneously, allowing for much higher throughput as GPU slots are filled immediately as requests complete. For example, Microsoft Research's Orca demonstrated that continuous batching could achieve a 36-fold improvement in throughput for a 13 billion parameter model by removing the synchronization barriers that static batching imposes. However, this method requires careful memory management to track active requests and ensure efficient processing without stalling the GPU. Finally, we must consider how tools like TensorRT LLM optimize inference through techniques such as kernel fusion, weight quantization, and innovative attention computation methods. NVIDIA's Triton Inference Server provides a robust serving layer that supports dynamic batching, model ensembles, and back-end abstraction, enabling us to deploy these models effectively. In summary, achieving over 80% model flops utilization requires us to eliminate bottlenecks throughout the entire system. Factors such as memory bandwidth, communication overhead, and kernel launch latencies can significantly impact performance. As you learn more about these systems, you will gain insights into how to balance these trade-offs and design robust, efficient architectures for LLM inference. In this chapter, we will explore the operation of Kubernetes clusters that are scaled to over 5,000 nodes and more than 150,000 pods. Our main focus will be on understanding the performance limits of the control plane, the throughput of the scheduler, the overhead introduced by network plugins, and the strategies for placing workloads on GPU infrastructure. As you progress to the L8DE level, you'll need to design Kubernetes systems that are resilient to control plane failures, can handle rapid scaling events, like going from 0 to 1,000 pods in less than 60 seconds, and maintain service-level objectives during node failures and rolling upgrades. By the end of this chapter, you will gain insights into specific bottlenecks within etcd, the Kube scheduler, and container network interface plugins. You will also learn how to configure pod disruption budgets, implement horizontal pod autoscaling using custom metrics, and set affinity rules to ensure your systems are reliable in a production environment. Let's start with the control plane scalability, which is fundamentally limited by etcd, the distributed key value store that holds the state of the cluster. etcd can handle roughly 10,000 writes per second, and while it can technically grow beyond its recommended maximum size of 8 gigabytes, doing so will lead to degraded performance. Each Kubernetes object, such as a pod, service, config map, or secret, consumes space in etcd, with a typical pod object using about 10 to 15 kilobytes. When you have around 150,000 pods, you're looking at 1.5 to 2 gigabytes of data in etcd just for those pod objects, which leaves some room for other resources. A critical issue arises when the write latency of etcd exceeds 100 milliseconds. This situation causes the API server to queue incoming requests, leading to cascading timeouts across various controllers. To mitigate this, production clusters typically run etcd on dedicated nodes equipped with NVMe SSDs and at least 32 gigabytes of RAM. They also schedule regular defragmentation during low-traffic periods, usually every 24 hours. It is essential to monitor certain metrics, such as the duration of etcd disk backend commits, ensuring that the 99th percentile stays below 25 milliseconds to maintain performance. Next, let's talk about the Cube Scheduler, which has a default throughput of around 100 pods per second. This throughput is determined by the duration of the scheduling cycle and the number of nodes that the scheduler must evaluate. Scheduling a single pod involves checking various predicates, such as node selectors, taints, and resource requests, as well as applying priorities like spreading and affinity rules across all candidate nodes. When you scale to 5,000 nodes with complex affinity rules, the scheduler's performance can become CPU bound. While the scheduler can run multiple threads, contention on shared data structures can limit its ability to parallelize tasks effectively. For environments that require rapid scaling, you can configure multiple instances of the scheduler with leader election, increase the API query per second limits, and use pod priority classes to ensure that critical workloads, such as large language model inference servers, can preempt less important batch jobs. However, if the node count exceeds 5,000, or if anti-affinity rules are in play, the evaluation complexity can grow significantly, leading to performance degradation. You will need to track metrics related to scheduling attempts and durations, aiming for the 99th percentile to stay below 500 milliseconds. Now let's consider the impact of network plugins on pod startup times and throughput. For example, using Calico with IPIP encapsulation can introduce a CPU overhead of 15 to 20% and limit throughput to 5 to 7 gigabits per second on 10 gigabit network interface cards due to the overhead of packet encapsulation and the evaluation of iptables rules. In contrast, Cilium leverages eBPF technology, which bypasses iptables altogether, allowing for packet filtering and routing directly in the kernel. This results in a higher throughput of 9 to 10 gigabits per second, with only about 5% CPU overhead. When managing 150,000 pods, iptables-based container network interfaces can generate millions of rules. This can lead to rule evaluation consuming several CPU cores per node and adding significant delays between 200 to 500 milliseconds to pod startup times. Cilium, on the other hand, stores network policies in BPF maps, which allows for constant time lookups regardless of the number of pods. For GPU workloads that require RDMA or GPU Direct, you can use the Multus CNI to attach secondary network interfaces directly to pods, effectively bypassing the overlay network. To maintain service-level objectives during node failures and scaling events, you will need to implement pod disruption budgets and horizontal pod autoscaling with custom metrics. A pod disruption budget specifies either a minimum number of available replicas or a maximum number of unavailable replicas, which helps prevent the cluster autoscaler or manual drains from terminating too many pods at once. For instance, if you have an inference deployment with 50 replicas and each pod handles 10 requests per second, setting a minimum available threshold at 40 ensures that even if a node upgrade affects 10 pods, the remaining pods can still manage the incoming load. Horizontal pod autoscaling can be configured to respond to custom metrics, such as GPU utilization and inference latency, allowing you to scale based on the actual characteristics of your workload, rather than just CPU or memory usage. You might set the autoscaler to target 70% GPU utilization and allow scaling from 10 to 100 replicas when the utilization exceeds this target for 60 seconds, incorporating a stabilization window to avoid excessive scaling fluctuations. Controlling workload placement is also crucial, especially for GPU workloads. You can use affinity and anti-affinity rules to ensure that pods are scheduled on the appropriate nodes. For example, you can specify that certain pods must run on nodes equipped. In this chapter, we delve into the critical skills necessary for system design and architecture selection, particularly in high-pressure interview scenarios. The goal here is to evaluate your ability to break down ambiguous requirements and translate them into concrete system designs that are backed by quantified constraints. You will need to articulate and defend your architectural choices when faced with probing questions from your interviewer. This exercise goes beyond textbook patterns. It requires you to think deeply about capacity planning, failure domains, and operational complexity. Let's explore some specific interview questions to illustrate these concepts. In the first question, you are tasked with designing a real time inference API for a large language model capable of serving 100,000 concurrent users while maintaining a P99 latency under 500 milliseconds. To tackle this, you start by calculating the load. With 100,000 users making an average of one request every 10 seconds, you arrive at 10,000 queries per second. For a 13 billion parameter model, each forward pass requires significant GPU memory and time. To meet the latency requirement, you budget your time across various components involved in processing the requests. You decide to implement continuous batching to optimize performance and mitigate issues like head-of-line blocking, which can occur when longer sequences delay shorter requests. Visualizing this design involves creating a flow diagram that illustrates how requests are handled, from the load balancer to the GPU pool, and detailing the capacity calculations that justify your GPU count. Moving on to the second question, you must choose between different frameworks for serving a multi-model ensemble, which includes an embedding model, a re-ranker, and a large language model. Your strong answer identifies RayServe as the best choice due to its ability to orchestrate across various models with different resource requirements. You explain that while Triton Inference Server excels in single-model scenarios, it lacks the necessary orchestration capabilities for multi-model pipelines. You also discuss the trade-offs involved, such as the slight overhead introduced by RayServe, which ultimately saves significant engineering effort. In the third question, you are asked to architect a multi-region deployment for a stateful recommendation service, ensuring global latency remains under 50 milliseconds. Here, you emphasize the physical limitations imposed by the speed of light, which makes single-region solutions impractical. You propose a strategy involving read replicas across multiple regions, allowing for local reads and eventual consistency. This design entails accepting some level of staleness in user embeddings to avoid the pitfalls of synchronous reads across regions. Next, you face a question about selecting a database for a high-write analytics pipeline. A strong response highlights ClickHouse as the optimal choice due to its ability to handle high write throughput and complex aggregations efficiently. You discuss its columnar storage and the advantages it brings in terms of compression and speed, while also acknowledging its limitations compared to other databases like PostgreSQL. In the fifth question, you design an auto-scaling strategy for a GPU workload that experiences bursty traffic. You recognize that with a 5-minute pod startup time, a solely reactive approach would be ineffective. Instead, you propose a 3-tiering scaling strategy that includes a warm pool of resources, predictive scaling based on historical traffic patterns, and a last resort reactive approach. The sixth question revolves around replication strategies for a financial transaction system. You argue for quorum writes as the best option, balancing the need for strong consistency with acceptable latency. You explain the risks associated with both synchronous and asynchronous replication and how quorum writes can mitigate those risks. Finally, the seventh question asks you to design a caching strategy for a social feed with millions of active users. You recognize the importance of caching in managing the load generated by hot posts and propose a multi-tier caching system that optimizes access times while minimizing database load. Through these questions, you not only demonstrate your technical knowledge, but also your ability to think critically about system design, making trade-offs, and anticipating potential failure modes. This chapter is about building a mindset that is essential for tackling real-world challenges in system architecture. In this chapter, we will delve into a crucial aspect of system design and maintenance, diagnosing production failures and managing scaling incidents. This involves not only identifying the symptoms of a problem through metrics, logs, and traces, but also architecting both immediate fixes and long-term solutions to prevent recurrence. As you prepare for interviews, it's essential to demonstrate your ability to trace issues back to their root causes, especially in complex distributed systems. You'll need to understand how failures can propagate and design your systems to be resilient and scalable. Let's start with a scenario where your large language model serving cluster experiences a sudden spike in latency. Imagine this. The P99 latency jumps from 200 milliseconds to a staggering 2000 milliseconds. Meanwhile, your GPU utilization drops significantly from 85% to 40%. And although the request rate remains steady at 5,000 requests per second, the CPU usage on your inference pods shows high input-output wait times. Additionally, the network traffic has doubled. What could have caused this? A strong answer would recognize that the increase in latency and the drop in GPU utilization suggest a shift in how requests are being processed. The doubled network ingress indicates that the average request size has increased, likely due to longer context lengths in the input data. The high input-output wait times imply that the system is struggling to process these larger requests, likely because the tokenizer or model loading process is overloading the disk, causing delays. Immediate mitigation strategies could include enforcing strict input length limits at the API gateway, increasing CPU resources for the inference pods, and implementing a caching mechanism for tokenized inputs. For long-term resolution, you might consider routing requests based on their context lengths and optimizing how your system handles memory to prevent future issues. Next, consider a situation where your Redis cache cluster fails. This failure leads to a dramatic increase in load on your PostgreSQL database, causing a cascade of failures throughout your application. The immediate response to such a situation would involve understanding how the cache was handling most of the read traffic and how its loss affects the database's capacity to manage connections. A strong response would focus on deploying fallback mechanisms for non-critical reads, reducing the number of application pods to limit the connection overload, and enabling connection queuing on the database. Long-term strategies might include implementing a tiered caching system and ensuring that your application can gracefully handle similar failures in the future. Another scenario involves corruption in your etcd database within a Kubernetes cluster. This can lead to scheduling issues and incorrect deployments. A robust answer would include identifying the affected resources quickly, using etcd commands, and restoring them to a healthy state. Long-term solutions would emphasize the importance of data corruption detection and regular backups to prevent similar issues from occurring. As we move to the topic of DDoS attacks, imagine your service is suddenly overwhelmed with malicious traffic. The immediate action here involves leveraging your cloud provider's DDoS protection services to filter out harmful traffic before it reaches your network. Additionally, implementing rate limiting and deploying a web application firewall can help manage the situation. For future resilience, serving static content through a content delivery network and maintaining a robust response plan for such attacks would be essential. In another case, you might face memory leaks in your GPU inference pods, leading to out-of-memory kills. A strong diagnosis would pinpoint the unbounded data structure causing the leak, and immediate fixes could involve implementing a bounded cache with eviction policies to manage memory usage effectively. Long-term strategies would focus on externalizing request metadata to a distributed tracing system and setting up alerts for memory usage. Lastly, consider the challenge of database replication lag, which can result in stale reads for your application users. A strong response would identify that the bottleneck lies in the single-threaded write-ahead log replay on replicas. Immediate fixes could involve routing read queries to the primary database temporarily, while long-term solutions might include upgrading to a version of PostgreSQL that supports parallel log application and designing your application to tolerate eventual consistency. Through these scenarios, the key takeaway is that understanding the underlying mechanics of your systems is vital. By analyzing symptoms, implementing immediate fixes, and designing for the future, you can ensure your systems are resilient and capable of handling the demands placed upon them.